Greetings, sir. Today I am going to take you through one of the most important fundamental problems in the history of artificial intelligence, the blocks world problem. Now, at first glance, it sounds almost trivially simple. You have a few colored blocks, a table, and a robot arm. The job is to rearrange the blocks from one configuration into another. But don't let that simplicity fool you. Because inside this tiny world lives the full machinery of AI planning, logical reasoning, heuristic search, and automated decision making. Now, moving on to what is the blocks world problem. So, formally, it is a micro world planning domain. Imagine a flat table. On that table sits a collection of cubic blocks labeled A, B, C, and so on. Above the table hangs a single robotic arm. The arm can pick up one block at a time and either place it on the table or stack it on top of another block. The AI's job is to take the current arrangement of blocks, the initial state, and figure out the exact sequence of arm movements needed to reach a desired goal arrangement. That sequence is called a plan. What makes this environment particularly well suited for studying AI is its properties. Look at this right side of the slide. The world is fully observable. The AI always knows exactly where every block is. It is deterministic. Every action produces a guaranteed predictable outcome. It is static. Nothing changes unless the arm acts, and it is discrete. There are a finite number of possible configurations. These properties make it a clean laboratory for testing planning algorithms. But here is the catch listed at the bottom of the definition. Despite looking simple, finding the optimal plan for blocks world problem is actually NP hard in the general case. The problem scales extremely badly, and that's what makes it genuinely interesting for AI researchers. Now, moving on to its physical components. Before we go into the AI logic, let's make sure we are clear on every element of this world. There are four things to understand. First, the block themselves. These are uniform cubic objects A, B, C, and so on. Each block occupies exactly one position. A block can either sit directly on the table or sit directly on top of exactly one another block. Crucially, blocks cannot be placed side by side, only vertically stacked. In the classic formulation, all blocks are identical in size and weight. Second, the table. Think of it as an infinite flat surface. It can hold any number of blocks simultaneously. When a block is resting on the table, we say the predicate on table is true for it. The table never moves, it is a fixed reference point for everything else. Third, and the important one, the robot arm. It is a single gripper. It can hold at most one block at a time. When it's holding something, the system knows because the predicate holding X is true. When it's empty, arm empty is true. Crucially, the arm acts instantaneously. In the symbolic world, there is no travel time, no momentum, no hesitation. It either holds something or it doesn't. Finally, the world state. This is a complete snapshot of every block's position at any given moment. It is described as a set of logical predicates. Two states are only considered the same if every single predicate matches. And as we will see in a few slides, with just n blocks, the number of possible states explodes super exponentially, which is where the real challenge begins. Now, moving on to the predicate logic and state representation. Let's look at how the AI actually describes this world in language it can reason about. The answer is predicate logic. Look at the table on the left. There are 5 core predicates, 5 statements the AI uses to describe the world. On x, y, block x is directly on top of block y. On table X, block X is resting directly on the table. Clear X, this is a crucial one, it means nothing is on top of block X. Holding X, the robot arm is currently grasping block X. And arm empty, the arm holds nothing. Note this one takes no argument, it's simply true or false. Now look at the example on the right. We have a tower C on top of B, B on top of A, and D sitting separately on the table. This is exactly how the AI sees the world, not as a picture but as a set of logical facts. Every single action changes some of these facts, and the planner's job is to find the right sequence of actions to transform the current fact set into the goal fact set. Now, moving on to the constraints and rules of the block worlds problem. With the vocabulary in place, let's talk about the rules, the laws that govern what the robot arm can and cannot do. There are four constraints, and each one has a real physical motivation. Rule 1: one block at a time. The arm has a single gripper, it simply cannot hold two things at once. The impact is that everything must happen sequentially. You cannot solve two sub goals in parallel with a single arm. Rule 2: a block must be clear to move. If another block is resting on top of your target, you cannot grab it from above. The implication is that deep towers must be taken apart from the top towers before you can access the block you actually want. The arm must be empty before it picks up, is rule 3. You cannot grab a second block without holding the first. This means every pickup action must be preceded by either putting the current block down or stacking it somewhere. Rule 4: the destination must be clear to stack. You cannot place a block onto another that already has something sitting on it. The planner has to explicitly clear its target before using it as a base. Notice the green and red panels at the bottom of each card. They show exactly what is allowed and what is not. These constraints turn out to be the source of all the interesting planning challenges we will see in the coming slides. Now the scripts operator. The four actions the robot arm can execute, each defined precisely by three lists. Each action has preconditions, add effects, and delete effects. Preconditions are the conditions which have to be true before the actions can execute. Add effects is something what becomes true after the action, and delete effects is something what becomes false after the action. Now, the first one, pick up X. To pick up block X from the table, three things must be true. X must be clear, X must be on table, and the X arm must be empty. After execution, holding X is added, and clear X, on table X, and arm empty are deleted. Now the put down X, the reverse. You only need to be holding X. Afterwards, the block is back on the table, it's clear, and the arm is empty again. Now stack X, Y. Place the held block X onto block Y. You must be holding X and Y must be clear. Afterwards, X is on Y. X is now clear, nothing on it yet, and the arm is free. Y is no longer clear. Unstack X, Y. Pick up X from the top of Y. X must be clear, X must be on Y, and the arm must be arm empty. Afterwards, you are holding X and Y is now clear. These four operators, pick up, put down, stack, unstack, are the complete vocabulary of the robot arm. Every plan is just a sequence of these four operations. Now the state, space, and complexity. Look at the table on the left. With just two blocks, there are only three possible states. With 3 blocks, 13. With 5 blocks, 501. And with 10 blocks, approximately 400 million states. And with just 20 blocks, we are talking about 10 to the power of 33, a number that dwarfs the number of atoms in the human body. This is super exponential growth, and it creates very real computational problems. On the right, we have 5 reasons why block world is genuinely hard. First, super exponential growth. Exhaustive search simply stops being feasible around n equals 7. Second is the sub-goal interference. You cannot solve each sub-goal independently and concatenate the results. Third, reversibly cost. A greedy planner that makes locally good moves can end up in infinite loops, undoing and redoing the same actions. Fourth, it is NP hard in the general case. Finding the optimal plan everything is probably hard. And fifth is a high branching factor. At every stage, the number of legal next moves grows with n. Without intelligent search, the tree becomes impossibly large. This is why good algorithms and good heuristics matter enormously in this domain. Now, moving on to the search strategies. So, how does an AI actually find a plan through this enormous state space? Let's look at 6 search strategies. The first one is BFS. It will always find the shortest plan if one exists. For the depth first search, it is much more memory efficient. It only stores the current path, but it's not optimal. It may find a very long plan before finding a short one. Moving on to the A star search, it is the gold standard in practice. With an admissible heuristic, it is both complete and optimal. It expands nodes in order of estimated total cost, focusing effort where it's most likely to pay off. Now, moving on to the iterative deepening, uh, it solves A star's memory problem by combining it with DFS. It runs multiple depth limited searches with increasing cost thresholds. Now the next is hill climbing. It is extremely fast but dangerous. It always moves towards the state that never looks better by the heuristic, never backtracking. Now the last one is strips or goal stack. It is domain aware. It doesn't explore states randomly but reasons backwards from the goal using means ends analysis. Very efficient, but as we will see, it has a fundamental weakness on certain problem structures.
Now let's understand heuristics. A heuristic is a smart way to guess how far we can go from the goal. It helps the algorithm choose the best path instead of checking every possibility. For A star search to work properly, the heuristic should not give a higher value than the real answer, and it should behave in a consistent way. Now we are looking at different types. First, misplaced block. Here we simply count how many blocks are not in the correct position. This is very easy to use, but it is not very accurate. Second is the block out of order. Here we check whether blocks are placed in a correct order. This is better because it understands stacking. Third is depth. This checks how many blocks are on the top of the block. If a block is buried under others, we need extra steps to reach it. Finally, there is perfect heuristic, which gives us the exact number of steps, but in real problems we cannot calculate it. So overall, better heuristics help us to reach the goal faster and reduces time. Now let's understand this with an example. On the left side we have the initial arrangement, in the center we have the goal arrangement. To move from the start to the goal, we follow these steps. First we unstack C from A, then we put the C on the table and pick B and place it over on C. Then we pick A and then place it over on B. So in total it takes 6 steps to reach the goal. The important idea here is we must clear the top blocks first before placing others. We cannot directly move A because C is blocking it. This example shows that planning must be done step by step in correct order. Now, this explains the Sussman anomaly. It is the famous problem in AI planning. It shows that we cannot solve goals one by one. For example, if we first try to achieve A on B and then try to achieve B on C, we may need to remove A again. So the first goal gets disrupted. This means the simple method of solving one goal at a time does not work. Instead, we must plan steps in a combined and a proper order. This concept is important because it shows that planning is more complex than it looks. Now we have the goal stack algorithm. Now let's see how the goal stack planning works. This method uses a stack to manage goals. Step by step, we'll get to know about this. First, we put the main goal into the stack. Then we break it into smaller goals. Then we find actions that can achieve each goal. Then we check that what conditions are needed before doing these actions. After that, we complete those conditions, we perform the proper action that is needed. This process continues again and again until all goals are completed. So basically, we solve the problem step by step from top to bottom. But this method has a limitation. It does not work well in complex situations like the Sussman anomaly. Now let's understand the PDDL. PDDL stands for Planning Domain Definition Language. It is used to describe planning problems in a standard way. It has two main parts. First, the domain file. This contains rules, actions, and conditions. Second, the problem file. This contains the starting state and the goal state. This separation is used because we can use the same rules for many problems. PDDL is used in modern AI systems and competitions because it helps different systems solve the same problem and compare their performances. Now we get to the real world application, like how this is used in the real life. Even though block world looks simple, its ideas are used in many real systems. In warehouse robotics picks and place items in a correct order. In surgical robots, machine plans safe movements of all the tools that are used in the surgery. In manufacturing, machines follow step by step assembly process. In logistic and cargo, containers are stacked in a correct order. All these systems follow similar ideas, doing actions step by step, following rules, and reaching a goal efficiency. So, this concept is very useful in real world applications. To conclude, block world is a very basic but important problem in AI. It helps us understand how machines plan actions. We use logic, search algorithm, and heuristic to solve it. Some situations, like Sussman anomaly, make planning more difficult. Heuristic help us to find solutions faster. PDDL is used to describe planning problems in modern systems, and these ideas are used in real world applications like robotics and logistics. So, even a simple problem like this helps us understand complex AI systems. Thank you very much for your time.